Hello everyone, welcome to the video lecture of this course finite element method. So this is the fifth module that we are continuing now, and in the earlier lectures we have discussed the concept of the isoparametric elements, then how to calculate the Jacobian matrix, how to calculate the stress strain relationship matrix, then the calculation of the local coordinates. All these things were discussed earlier, and we have solved different numericals to solve these different things like the Jacobian matrix, then different stress strain relationship matrix, then element stresses, all these things. Then in the earlier lecture we have discussed the concept of the serendipity elements and Gaussian quadrature. There we have seen the formula for the shape functions, and now in this lecture we will discuss different numericals, and there we will solve some numericals based on the concept of the Gaussian quadrature. One table regarding the Gaussian quadrature we have discussed in the earlier lecture. Now based on that formula and taking the help of that table, we will today solve different numericals based on the Gaussian quadrature. Okay, so let us start this lecture. Now this is the course objective and course outcome of this subject, so which is known to us, and this is the COPO mapping for this course. Now this is actually the table and the formula related to the Gaussian quadrature that we have discussed in the earlier lecture. So here we can see that the formula for this Gaussian quadrature, it is minus 1 to 1 fx dx. This is equals to I summation I equals to 1 to n wi fxi. Now this fxi, it is the Gauss sampling points, and wi, it is the corresponding weight function for different number of points. Now this table, which you can see here as table number 5.1, here corresponding to the number of points the locations are given, and corresponding to that the different weights, these are also provided. Now these values of this table we need to remember, and we will use all these values for the corresponding number of points to solve the problems related to this Gaussian quadrature. Now let us start the problem number 1. Here it is said that we need to evaluate integration minus 1 to 1 x to the power 4 plus x square dx by applying 3-point Gaussian quadrature. So how to perform this numerical, how to proceed in this numerical related to this Gaussian quadrature. The integral I here, it is minus 1 to 1 x to the power 4 plus x square dx. So that means the function fx, it is x to the power 4 plus x square, and we need to evaluate this integral by using Gaussian quadrature with 3 Gauss points. Now for 3-point Gaussian quadrature, x1 is root under 3 by 5, that is 0.77459, x2 is 0, and x3 is minus root under 3 by 5. So from where we got these values, these are we have got from here in this table. We can see for corresponding to the number of points 3, the value of x1 and x3, these are given as plus minus root under 3 by 5. That means the plus value, it is for x1, That means x1 is plus root under 3 by 5 and x3 is minus root under 3 by 5, and x2 it is 0. Now corresponding to x1 and x3, the weight W it is 5 by 9, that means 0.555, and corresponding to the location x2, the value of weight W it is 8 by 9, that is 0.88. So these values we will use in this numerical. So here we have seen that the value of x1 it is plus root under 3 by 5, x2 is 0, and x3 is minus root under 3 by 5. So that means minus 0.77459. Now corresponding to x1 and x3, the value of w1 and w3, these are same, and these are actually 5 by 9, which is 0.555, and corresponding to x2 0, the value of the weight w it is 8 by 9, which is 0.888. Now the integral which is given here fx, it is x to the power 4 plus x square, it is the function here. So fx1 it can be calculated as x1 to the power 4 plus x1 square. Now the value of x1 we have already identified from the table, which you can see in the earlier slide, where x1 is given as plus root under 3 by 5. So this value we have entered here, and finally we have calculated the value of the function when x is x1. So what we are getting, that fx1 it is 0.96. So that means w1 into fx1 it can be computed as 0.96 into 0.555, because the value of w1 it is 0.555, that is 5 by 9. So w1 into fx1 it is 0.5333. This is our equation number 1. Next, in the similar manner, we need to calculate the value of fx2. So the equation is x2 to the power 4 plus x2 square. The value of x2 that we have identified from the table, it is 0. So that means fx2 this is 0. Now if we multiply this value of x2 with the corresponding weight w2, then we are getting w2 into fx2, this is 0. So this is our equation number 2. So in this similar manner, we need to calculate fx3. So fx3 is x3 to the power 4 plus x3 square. Now the value of x3, it was, from the earlier slide you can get that it is minus root under 3 by 5. So the value of x3 it is minus 0.7745 to the power 4 plus minus 0.7745 to the square. So the value of fx3 it is coming as 0.96. So if we multiply this fx3 with the corresponding weight, then w3 into fx3 we are getting as 0.5333, which is our equation number 3. Now, as this is a 3-point Gaussian quadrature, so we need to add these 3 different equations. So that means finally we will get w1 fx1 plus w2 fx2 plus w3 fx3. So the final result we are getting is 1.0666. So this is the final result for the integral that we have got here using the Gaussian quadrature concept. Now, how to verify this result? The verification is simple. We need to perform the integration here, that is minus 1 to 1 x to the power 4 plus x square dx. So for the first one, that is x to the power 4 dx, it is 1/5 x to the power 5, and for the second part it is x cubed by 3, and the limit it is minus 1 to 1. Now if we do the simple integration, then finally we are getting the value. It is coming as 1.06, which is the same that we have got from the Gaussian quadrature concept. So the calculation done by the Gaussian quadrature and by the simple integration, these are coming same. So that means this result is verified. Let us discuss the next numerical. So what it says, that we need to evaluate the integral minus 1 to 1 x to the power 4 minus 3x plus 7 dx. So here is one interesting thing, that in this numerical it is not said that how many Gaussian quadrature sampling points we need to consider. So that one we need to find here. Now here the integral I is minus 1 to 1 x to the power 4 minus 3x plus 7 dx. So that means fx, this is equals to x to the power 4 minus 3x plus 7. So we need to evaluate the integral by using the Gaussian quadrature. Now first we need to find the number of the sampling points here for the Gaussian quadrature. And here the given integrand is a polynomial of the order 4. So for the exact integration, 2n minus 1, this is equals to 4. So that means n equals to 2.5. So that means the calculated number of sampling points should be rounded up to the nearest integer value. So that means n equals to 3. That is, in this problem we should use the 3 sampling points for the Gaussian quadrature. So this is the process by which we have identified the number of the sampling points based on the polynomial of the order. Now for the 3-point Gaussian quadrature, the value of x1, x2, x3 and w1, w2 and w3, we need to identify, or we need to select from the table for the Gaussian quadrature. And we have seen from the table that if we go back to the table earlier slide, then from the number of points 3 we can see that x1 and x3, this is plus minus root under 3 by 5. So that means for x1 it is plus root under 3 by 5 and for x3 it is minus root under 3 by 5. And corresponding to the x1 and x3, the weight it is 5 by 9. Then for x2 it is 0, and corresponding to this x2 the weight it is 8 by 9. So these values for the 3 sampling points of the Gaussian quadrature we need to use here in this second numerical. So first we have written the values of x1, x2, x3, then w1, w2 and w3, all these values we have written from the table. Now the fx, it is given here as x to the power 4 minus 3x plus 7. So first we need to calculate fx1, which we are getting as x1 to the power 4 minus 3x1 plus 7. So if you put the value of x1 from the table, then we are getting that fx1 it is 5.036. Now if x1 is 5.03, then w1 into fx1 it is 0.55 into 5.03, which is coming as 2.797, which is our equation number 1. Now in this similar manner, we need to calculate W2 into fx2 and W3 into fx3, because we are considering the 3 sampling points here. So fx2, it will be x2 to the power 4 minus 3x2 plus 7. If we put the value of x2 as 0, then we are getting fx2 as 7 only. So W2 into fx2, this is coming as 6.222. So this is our equation number 2. Now in this similar manner, we need to calculate the value of fx3. So fx3 is x3 to the power 4 minus 3x3 plus 7. So putting the value of x3 here, we are getting that fx3 is coming as 9.683. So that means W3 into fx3, it is now coming as 5.379, and this is our equation number 3. Now if we add these 3 different equations for the 3 sampling points of the Gaussian quadrature, and if we sum them up, then we are getting the final value of this integral. It is coming as 14.399. Now we need to verify this result by performing the direct integration here within the limit minus 1 to 1. So for x to the power 4, it will be x to the power 5 by 5. Then for minus 3x, it is minus 3x square by 2. And for 7 dx, it is only 7x. And this we need to perform, and we need to find the value within the limit minus 1 to plus 1. So that means if we do the simple integration, then finally after 2 steps, we are getting the value as 14.4. So which is almost same with the value that we have got through the Gaussian quadrature concept. Let us move to the next numerical. We need to evaluate the integral by using Gaussian quadrature, and the problem given is minus 1 to 1 x square dx. Now the integral given, it is minus 1 to 1 x square dx, so fx is only x square. Now we need to evaluate this integral using the Gaussian quadrature concept. So again in this numerical, you need to find the number of the sampling points, because it is not mentioned in the question. So as performed in the earlier numerical also, the given integrand is a polynomial of the order 2. So for exact integration, 2n minus 1, it is only 2. So 2n is 3 and n equals to 1.5. So the calculated number of sampling points should be rounded up to the nearest integer, which is 2. So in this problem, we should use the 2 sampling points. So this is the procedure following which we have identified the number of the sampling points for this given numerical, which is 2. Now we need to refer the table regarding the Gaussian quadrature for number of points as 2. So let us move back to the table. So here we can see that for the number of points 2, the location x1 and x2, these are plus minus root under 1/3. So that means x1 is plus root under 1/3 and x2 is minus root under 1/3. And the value of the weight, that is w1 and w2, corresponding to this x1 and x2, this is 1. So these values we will use here in this numerical. So x1, it is plus root under 1/3, that is 0.577, and x2 is minus root under 1/3, which is minus 0.577. And w1, it is 1, and w2 is also 1. Now fx, this is given as x square, so that means fx1, it is x1 square. So the value of x1 it is we have got from the table, that is plus root under 1/3. So the fx1 it is coming as 0.333. Now if we multiply this with the corresponding weight, which is 1 actually, so the value of w1 into fx1 it will be same as the fx1. So that means the w1 into fx1 we are getting as 0.333, which is our equation number 1. Now in this similar manner, we need to calculate the value of fx2. So this is actually x2 square, and the value of x2 it is given from the table, which is minus root under 1/3. The value we are getting is same with the x1 fx1, so this fx2 is coming as 0.333. Now as the value of w2 is 1, so w2 into fx2 it will be also same, which is 0.333, and it is our equation number 2. Now to find the value of the given integral, we need to add these two different equations, that is we will add w1 into fx1 and w2 into fx2. That means the final value we are getting here is 0.666. So this is the result here, which is 0.666 or minus 1 to 1 x squared dx. So we can also verify this one by doing the simple integration. It will be x cubed by 3, and the integration should be minus 1 to 1. The limit of the integration it is minus 1 to 1 for x cubed by 3. Now let us move to the next numerical. Now we need to evaluate minus 1 to 1 e to the power minus x dx by applying 3-point Gaussian quadrature. So here it is mentioned the number of points, number of sampling points for the Gaussian quadrature, that is 3. Now the integral I it is given here as minus 1 to 1 e to the power minus x dx. So that means fx is e to the power minus x. Now we need to evaluate this integral by using the 3-point Gaussian quadrature. Now for the 3-point Gaussian quadrature, to find the value of x1, x2, x3 and their corresponding weights, that is w1, w2 and w3, we need to refer to the table. So from the table we have got that the value of x1 it is plus root under 3 by 5, it is 0.77459, and the value of x2 is 0, and the value of x3 it is minus root under 3 by 5, so it is 0.77459. And the corresponding weights, that is w1 is 5 by 9, it is 0.555, then w2 is 8 by 9, it is 0.8888, and w3 it is also 5 by 9, which is 0.555. So all these values of x1 and x3, x1, x2, x3 and w1, w2 and w3 we have got from the table of the Gaussian quadrature. Now to find the value of the fx, we need to first find the value of fx1, which is e to the power minus x1. So fx1 is 0.46088. If we multiply this with w1, which is 5 by 9, then we are getting w1 into fx1 it is 0.25604. This is our equation number 1. Now in this similar manner, we need to calculate w2 into fx2 and w3 into fx3. So the value of fx2 it is coming as e to the power minus x2, which is e to the power minus 0, which is actually 1. Now if it is multiplied by w2, then finally we are getting the value of w2 into fx2 as 0.888, which is our equation number 2. Next, the value of fx3 it is e to the power minus x3, that means e to the power 0.77459, which is coming as 2.16971. So the value of w3 into fx3, this is coming as 1.20539. So this is our equation number 3. Now to find the final value of this integral, we need to add these three different equations. It is w1 fx1 plus w2 fx2 plus w3 fx3. This is equals to 2.350. So this is the final result of this given integral. We can also verify this by performing the simple integration for this e to the power x within the limit minus 1 to 1. So let us move to the next numerical. So we need to evaluate the integral I equals to minus 1 to 1 cos pi x dx by applying 3-point Gaussian quadrature and compare with exact solution. Now the integral I is given minus 1 to 1 cos pi x by 2 dx. So that means fx is cos pi x by 2. Now we need to evaluate the integral. By using the 3-point Gaussian quadrature, and we need to compare with exact solution. Now for 3-point Gaussian quadrature, we know the value of x1. It is root under 3 by 5 plus root under 3 by 5, which we got from the table. Then the value of x2, it is 0, and the value of x3, it is minus root under 3 by 5, so which is minus 0.77459. And the corresponding weights, that is w1, it is 5 by 9, and w2, it is 8 by 9, and w3 it is 5 by 9. So these are the values that we have got from the table. Now here the value of fx, it is cos pi x by 2. So that means fx1, it is cos pi x1 by 2. So which is coming finally as 0.3467. If we multiply this fx1 with w1, then we are getting the w1 into fx1, it is 0.1926174, which is our equation number 1. In this similar manner, we need to first calculate the fx2, which we are getting as 1, and if we multiply this with the corresponding weight w2, then we are getting w2 into fx2 as 0.888, which is our equation number 2. Next, for fx3, it is cos pi x by 3, and putting the value of x3 here, we have calculated the value of fx3, which is 0.3467. Now that means the value of w3 into fx3, this is coming as 0.1926, which is our equation number 3. Now if we add these three different equations, that means w1 fx1 plus w2 fx2 plus w3 fx3, then finally we are getting the value of this integral as 1.2741. That means minus 1 to 1 cos pi x by 2 dx, it is coming as 1.2741. Now we need to compare this value that we have got from the Gaussian quadrature process with the exact solution. So the exact solution, we need to perform the simple integration, that is minus 1 to 1 cos pi x by 2, it is sin pi x by 2 divided by pi by 2, and the limit will be minus 1 to 1. So finally the value we are getting here is 1.273. So here you can see that the result which we got by 3-point Gaussian quadrature and by exact method, these are almost similar. So these are the 5 different numericals that we have discussed in this lecture with the help of the concept of the Gaussian quadrature and the table related to the number of points, location and the corresponding weights of the Gaussian quadrature. So that formula of the Gaussian quadrature and that value of the number of points, then the location and the corresponding weights from that table, we need to remember to solve the different numericals of this Gaussian quadrature. Okay, and so this is the end for this lecture.